Given a positive real number p, call a real sequence a sub n p rapid if for any epsilon greater than 0 there exists a positive integer capital N such that the distance between a sub n plus 1 and a sub n is less than epsilon over n to the p for any positive integer n greater than or equal to n. For what values of p greater than 0, if any, does a real sequence being p rapid imply its convergence? Well, this is a real analysis question dealing with a convergence of a sequence, so I think it is only natural that we review some of the basic definitions and a theorem related to a convergent sequence on R. First of all, let's review what it means for a sequence to converge. So a sequence converges if for every epsilon greater than 0, there exists capital N, being a positive integer, such that let's say a sequence a sub n converges to A, such that the distance from a sub n to A is going to be less than epsilon for all n greater than or equal to capital N. So a sequence a sub n converges to A if the terms of the sequence a sub n and A become as close as we want for large enough values of n. Now there is a second important definition that I want to talk about, and if you have studied real analysis, you know what it's going to be by looking at this definition, because this definition very closely resembles the definition of a Cauchy sequence. So let's write down the definition for a Cauchy sequence. A sequence a sub n is Cauchy. Now the definition is almost the same as the definition of the convergence, except that we look at a sub m and a sub n, and for all m and n greater than or equal to n. So a sequence is Cauchy if the terms of the sequence can be made as close as we want for large enough values of m and n. Now it is a very beautiful and extremely significant result from real analysis that in R, so I have to specify that. So on the real line, a sequence converges if and only if it is Cauchy. So in R, these two conditions turn out to be identical. In case you're curious, there are metric spaces, so not R, but there are metric spaces such that being a Cauchy sequence by itself is not enough to guarantee convergence. But that's of course beyond the scope of this video, and if you're interested, I highly encourage you to look it up. Before we continue on, I'd like to take this time to recognize Mr. L for being the very first person to correctly answer this problem. And Mr. L responded with an outstanding solution, which is also the solution presented in this video. A huge shout out to Mr. L. Anyway, hopefully you see the similarity between the definition of the Cauchy sequence and the definition of a p-rapid sequence. Now for p-rapid sequence, note that we don't have epsilon, we have epsilon over n to the p power, but more importantly, we don't have a sub m minus a sub n, instead we have a sub n plus 1 minus a sub n. So we're not comparing any two terms beyond this specific threshold of capital N, we are only comparing two consecutive terms. For some of you, your intuition may make you ask, why wouldn't a p-rapid sequence always imply its convergence? Why wouldn't a sub n and a sub n plus 1 getting closer and closer to each other be enough to guarantee convergence? Well, can you think of a sequence such that the difference between the terms gets smaller and smaller? In fact, the difference between the terms goes to 0, yet the sequence fails to converge. The harmonic series, or more specifically, the partial sum of the harmonic series may come to your mind. So let's say a sub n is sum from k equals to 1 to n of 1 over k. It is well known that limit of a sub n is actually infinite, so the harmonic series diverges. Yet the difference between a sub n plus 1 and a sub n is going to get smaller and smaller. So after seeing this, you may say, maybe p-rapid sequence does not have to converge. Still, it looks like we are onto something, so let's examine this a little bit more closely. Let's first think about when this a sub n, or the sum from k equals to 1 to n of 1 over k, is actually p-rapid. Well, let's start by realizing that a sub n plus 1 minus a sub n, if a sub n is the partial sum of the harmonic series, is simply going to be 1 over n plus 1. because to go from a sub n to a sub n plus 1, we are adding the term 1 over n plus 1. And when it's 1 over n plus 1, what values of p can we make this less than epsilon over n to the p for sufficiently large values of n? Well, let's look at this a little bit closely. Let's rearrange this as n to the p over n plus 1. And we see that for p between 0 and 1, limit as n goes to infinity of n to the p over n plus 1 is going to be 0, because the degree of the top is going to be the smaller than the degree of the bottom. Since this thing goes to 0 for large enough values of n, for large enough values of n, of course it can be made smaller than epsilon. Now, what happens if p is greater than 1? Well, in that case, limit of this quantity is actually going to be infinite, because n to the p is going to grow faster. And this means we cannot bound it to be smaller than epsilon for large enough values of n. Now the tricky case is what happens when p is 1? Well, in that case, the limit of this quantity is simply 1, because you have n over n plus 1, which is telling you that for large enough values of p, this thing is going to be close to 1. So if epsilon is, for example, 0.5, we cannot make n to the p over n plus 1 less than 0.5 for large enough values of n, because this entire thing is going to approach 1. So what is this telling us? Well, that's telling us that the a sub n, the partial sum of the harmonic series, is p rapid for every p between 0 and 1 exclusive, but is not p rapid for p greater than or equal to 1, including 1. This immediately shows us that p between 0 and 1 is not enough. If a sequence is p rapid for p between 0 and 1 exclusive, then it does not have to converge, because the harmonic series diverges. So the natural question that we have is, what happens if p is greater than or equal to 1? Something that we may conjecture, if you know about the p series or the Riemann zeta function, the basic definition of a Riemann zeta function, is that p greater than 1 might be the answer. Because, as you may know from the second semester calculus class, the sum from k equals to 1 to infinity of 1 over k to the p converges for p strictly greater than 1, but diverges for positive p less than or equal to 1. So you may expect something similar to hold, because in the definition of the Riemann zeta function we have 1 over k to the p, here we have 1 over n to the p. So there is a very close similarity, so maybe the answer is going to turn out to be the same. Now, if this series converges for p greater than 1, then a sub n must be Cauchy by this theorem from real analysis, that a sequence converges if and only if it is Cauchy. And since our expression a sub n plus 1 minus a sub n is very close to the expression in the definition of the Cauchy sequence, the natural thing to do is maybe form a bridge between these two expressions. So let's try to do so. So we want to show that a sub n minus a sub n can be made as small as we want if a sequence is p rapid with p greater than 1. So let me copy down the definition of a p rapid sequence. So that's when this thing a sub n plus 1 minus a sub n is less than epsilon over n to the p. So let's start by breaking this a sub n minus a sub n using triangle inequality to bunch up consecutive terms. So a sub n minus a sub n minus 1, a sub n minus 1 minus a sub n minus 2, and so on until a sub n plus 1 minus a sub n. Now here we are assuming, without loss of generality, that m is strictly greater than n. Note that if m and n are equal, if m is equal to n, this thing is 0, so of course it is less than epsilon, so we don't have to worry about the case. So when m is greater than n, we can break it down like this, and from here we can use the definition of the p-rapid sequence to bound each of these expressions even further, getting us less than epsilon over n minus 1 to the p, then epsilon over n minus 2 to the p, all the way to epsilon over n to the p. Can this thing be made as small as we want for large enough values of m and n? Well, realize that this thing is of course less than epsilon times the sum from k equals to 1 to infinity of 1 over k to the p, because here we're only looking at the values of k between n and m minus 1. And we know this thing is finite if p is greater than 1. So if p is greater than 1, we know this thing is less than epsilon times some finite number, which is telling us that a sub m minus a sub n can be made as small as we want because epsilon can be any number greater than 0. That's telling us that a sub n is Cauchy if it is p rapid for p greater than 1, which tells us that a sub n converges if it is p rapid for p greater than 1. So we are very close to being done. We have shown that p greater than 1, so if a real sequence is p rapid for p greater than 1, then it has to converge. And for p between 0 and 1 exclusive, then the real sequence being p rapid is not enough to imply its convergence. So the only value that we have to test is what happens at p of 1. Notice that we cannot use the harmonic series like we did to analyze positive p less than 1, because the partial sum of the harmonic series is not 1 rapid. It's not p rapid for p greater than or equal to 1. So here's what we need to rule p equals to 1 out. So if we want to say p equals to 1 does not work, we have to come up with a sequence such that it is 1 rapid but diverges. And one of the first things you may think of is, can we just modify the exponent in 1 over k? So can we think of a p series, so k equals to 1 to the n of 1 over k to the p, such that this thing is 1 rapid but it diverges? That does not really work, because if you increase this exponent by even a little bit, if it's k to the 1.00001, then a sub n is going to converge. Whereas if we lower it to 0.9999, then this thing is no longer going to be 1 rapid, as you can easily verify. So the main thing to realize is that partial sum of 1 over k to the p for any p is not going to be enough to rule out the case when p is 1. But it does give us some idea of what to do. So we want a sub n such that the denominator grows significantly faster, fundamentally faster than k to the first power, but not too fast, such that it does not lose its 1 rapid property. And one way of doing so, instead of increasing the power of k, is to multiply by natural log of k, because the natural log of k fundamentally grows slower than any k to the p for positive values of p. Now here is what I assert. I assert that if we define a sub n like this, it is 1 rapid, but it also diverges. Let's prove both of them really quickly. To show it's 1 rapid, realize a sub n plus 1 minus a sub n. Here it's going to be 1 over n plus 1 times the natural log of n plus 1. And we want to make sure this thing is less than epsilon over n to the first power. It's 1 rapid for large enough values of n. That's equal to n times n plus 1 times the natural log of n plus 1. But realize, as n approaches infinity, this thing is going to approach 0 because n over n plus 1 is going to approach 1, whereas the natural log of n plus 1 is going to increase without bound, which means that this thing can be made less than epsilon for large enough values of n. So this thing is 1 rapid. How do we show divergence? Well, before we show divergence, let's correct this to k equals to 2 to n, because when k is 1, the denominator is going to be 0. And we can simply let a sub 1 be 0. Now for this one, a test for convergence that may come to your mind is the integral test, because 1 over x times the natural log of x is easy to integrate. That's simply natural log of x. And if you remember, if the corresponding function 1 over x to the natural log of x is positive, continuous, and decreasing, then the integral and the series are either both going to converge or both going to diverge. And 1 over x times natural log of x certainly meets the criteria, so we can continue on, and this thing is obviously infinite. So we know a sub n diverges. So p equals to 1 does not guarantee convergence. So we have found that the answer to this question, the only values of p greater than 0 that guarantees convergence if a sequence is p rapid, is p greater than 1, and we are done.